Hello, welcome to Understanding Power Electronics. This is a second video in a set of two videos discussing DC to DC buck converter under continuous conduction mode. In the first video, we saw the basic operation of the converter and some waveforms. We will continue the discussion in this video. In the beginning of the video, we will go through what we discussed in part 1 briefly, just so that we don't abruptly start this video. In this video, we will understand how to calculate the ripple voltage value in the output capacitor. We will also go through the diode and switch voltage and current waveforms. Also, we will verify the input-output power balance under ideal conditions. And lastly, we will do an example problem to draw the buck converter waveforms, just so that our understanding will be strengthened. With those in mind, let's get started. The prequel video, as I mentioned, is the buck DC-DC converter CCM part 1. This is the buck converter circuit diagram. As I mentioned, we will briefly go through some of the points we learned in part 1. In case you haven't done this topic before, I would recommend that you go through part 1 first, so that you don't feel rushed in learning. First, let's plot the VA waveform. VA is the voltage at node A with respect to this common point. When the switch is on, A will be connected to Vin, the source. When the switch is off, inductor current freewheels through the diode and VA will be 0. So the VA toggles between Vin and 0. T on, T off and TS are the switching intervals of the converter. The average of VA is the output voltage. The LC filter filters all the switching components and lets the DC pass through. We showed in part 1 V0 equals dV in, where D is the duty cycle T on by Ts. Next, we can plot the inductor voltage. The plus terminal is always connected to A, but A swings between Vin and 0. The minus terminal is always connected to V0, which is a constant voltage. So we can plot the inductor voltage. It varies between Vin minus V0 during the T on interval and minus V0 during the T off interval. This voltage is applied to the inductor. The rate of change of inductor current will depend on this voltage. DIL by dt is VL by L, and we can plot the inductor current. It starts from some value I1, goes up at a rate of Vin minus V0 by L. Vin minus V0 is, of course, the voltage across the inductor during T on. And then when the switch is off, the voltage across the inductor is minus V0 and the current slope is minus V0 by L, and the current returns to I1 because we are under steady state. This is the inductor current waveform. One important parameter is delta IL, the peak-to-peak ripple current. Delta IL is the slope of the current times the interval, that is Vin minus V0 by L times T on. When we do that and then manipulate it a bit, we get delta IL to be Vin Ts by L d1 minus d, and which is the same as V0 Ts by L times 1 minus d. Next, in the earlier video, we saw the relationship between inductor, load and capacitor currents. Here I am plotting the inductor current again. Delta IL and the slope during on interval both are marked here. The inductor current can be written as a sum of the DC current or the average current and the AC current or the ripple current. So IL is IL average plus IL AC. Here is the IL average, that is the DC current. IL AC is the ripple in the inductor current. The DC current cannot flow through the capacitor. The capacitor will block the DC current under steady state. So the DC current flows through the load. A capacitor presents a low impedance path for the AC ripple current. So for all practical purposes, the AC ripple current flows through the capacitor. So the average current, IL average, flows through the load, IL AC flows through the capacitor. After all, the reason why we are using the capacitor is to filter the ripple current. So IL average equals I naught and IL AC equals IC. That is just a quick run through of what we learned in part 1. Now we will move on to the main topics of this video. First, we will see how to determine the ripple voltage in this capacitor. Next, we will see how to determine the output ripple voltage. So in order to do that, we will focus on the output side of the circuit, the LC filter and the load. This is a very important parameter. So many times limits are placed on how much this ripple can be. This defines how good a DC voltage we are getting. Let's consider the capacitor current. We just now saw how it is to be plotted. This is the delta IC, peak-to-peak capacitor ripple current, which is the same as the peak-to-peak inductor ripple current. We also know how to calculate this delta IL. Delta IL is V naught Ts by L 1 minus D. We wish to find the ripple voltage. We know current and voltage in a capacitor is related by this equation, IC equals C dVc by dt. In order to find the Vc, we have to integrate the current IC. Vc is 1 over C integral IC dt plus K. K is the constant part. This integral will determine the ripple voltage. The capacitor voltage can be divided again into two parts. Vc average, which is the output voltage. Vc average is V naught equals dV in. Vc average and the ripple part. And we are interested in the ripple part. We will first plot the ripple voltage and then I will explain how it comes about. The green waveform here shows the ripple voltage. I will mark additional time points T1 and T2 at the zero crossings of the capacitor current waveform. At T1, the capacitor current is 0. Since the capacitor current is 0, dVc by dt is 0. That means the slope of the capacitor voltage is 0. The slope of Vc is 0 here. And then between T1 and T2, the capacitor current is always positive. That means charge is always going into the capacitor. So because the capacitor current is always positive, dVc by dt will always be positive. At T1, the capacitor voltage is V1 and it rises to V2 at T2 continuously. At the end of the on period here, the IC current is maximum. Because IC is maximum, dVc by dt, the slope will be maximum. So here, capacitor voltage slope will be maximum. Between T2 and T3, a similar thing happens. Between T2 and T3, the capacitor current is always negative. The charge is always going out of the capacitor and the voltage will continuously fall because dVc by dt is negative. And at T3, once again, the current is 0. dVc by dt is 0. So the slope here is 0. The voltage returns to V1 because we are under steady state. The capacitor voltage rises from V1 at T1 to V2 at T2 and then falls back to V1 at T3. That's the end of the period there. So during this interval between T1 and T2, charge is going in. That charge is Q plus. Between T2 and T3, charge is going out of the capacitor. That charge is Q minus. Because the ripple voltage returns to the same value, Q plus should be equal to Q minus in magnitude. Q plus plus Q minus is 0. This is called charge balance. There is a video in this series on charge balance which goes into this in greater detail. You may wish to go through that video. We are interested in the peak-to-peak ripple voltage, which is V2 minus V1, the delta Vc. So if you take the capacitor current and integrate it between T1 and T2 and divide by C, you will get delta Vc. So 1 over C integral T1 to T2 IC dt, that is the capacitor ripple voltage. And integral T1 to T2 IC dt, that is Q plus. So this equals Q plus by C. So the charge going in or the magnitude of the charge going out divided by C will give you the peak-to-peak ripple voltage. As I mentioned, this is a very important parameter in deciding the quality of the DC voltage. Notice one simple trick we are doing. So far we assumed that the output voltage is constant, V0, pure DC. We found the inductor current, everything. And then we are saying now, wait a minute, inductor current has a ripple and that ripple current flows through the capacitor. So if the ripple current flows through the capacitor, there should be a ripple voltage. So we are acknowledging that the output voltage is not pure DC, but for inductor current calculation purposes, assuming that the capacitor voltage is constant is good enough. The ripple voltage is a secondary effect. The magnitude of the ripple voltage is quite small, less than 2%, less than 1%, even less in many cases. The ripple voltage is small enough that it does not affect the previous results. So our assumption of the output voltage being constant to determine the inductor current, that is perfectly all right. Now we wish to calculate the Q plus value. This triangle is identical to this triangle. You can check it up. The height of the triangle is delta IL by 2. The base of the triangle is half the period from T1 to T3, that is one period. So between T1 and T2, it is half a period. So the charge Q plus is half Ts by 2 delta IL by 2. So delta IL you can substitute and you can calculate this as half times Ts by 2 times V0 Ts by 2L times 1 minus D. That becomes equal to V0 Ts squared divided by 8LC times 1 minus D. We have assumed an ideal capacitor, so delta Vc is the same as delta V0. So this is the ripple in the output voltage also. So delta V0 by V0 is Ts squared by 8LC times 1 minus D. Now we will rewrite this equation in a slightly different way in order to understand it better. Ts is of course 1 over Fs, or switching frequency is 1 over Ts. L and C form a resonant filter. F0 is the LC resonant frequency, which is 1 over 2 pi root of LC. I can make use of these expressions for Fs and F0 and rewrite delta V0 by V0. I will put the final form. You can check it out by doing it on a piece of paper. Delta V0 by V0 is pi squared by 2 1 minus D F0 by Fs whole square. Now you can see that this L and C combination, it's a second order filter. Fs is the switching frequency or the exciting frequency of the resonant filter. F0 is the resonant frequency or the corner frequency of the filter. The switching frequency will typically be much higher than F0. So F0 by Fs will be a fraction less than 1, much less than 1 in fact. So when you square it, it will be even lower than 1. So essentially this shows how effective this LC filter is. And by keeping the Fs much higher than F0, we can reduce the ripple. So essentially what it means is you need to have higher L, higher C, or both. So we have now found the ripple voltage. But there is a caveat. There is a warning. We have assumed an ideal capacitor. Capacitors have parasitic elements associated with them. Sometimes they will matter, sometimes they will not matter, depending on your design. Depending on at what frequency you are operating, what type of capacitor you are using, and so on. So don't forget to check for ESR. A capacitor typically has a series resistance associated with it due to its construction. When the ripple current passes through, the output voltage will be the ideal capacitor voltage plus the ESR voltage. In some cases, in low frequency designs, ESR may be neglected. In high frequency switch mode power converters, you may not be able to neglect it, so you have to check it. You may ask, capacitors have leakage associated with them that can be represented by a parallel resistance. What about that? Such a parasitic resistor in parallel with the capacitor may not be an issue because the load is also parallel to the capacitor. So it will just get added up with the load. It might have a small effect on the load, especially under no load conditions. ESR, being a series resistance, can have a great effect on the output ripple voltage. The voltage drop in the ESR can be sometimes so significant, it may even overshadow the voltage drop in the ideal capacitor. In other words, the ripple voltage may almost be totally determined by the ESR alone. Another parasitic component that can be troublesome at high frequencies, maybe in a 1 megahertz converter, is ESL. As you can guess, that is equivalent series inductance. So a designer has to take into consideration or at least check for effects of ESL and ESR. Now we will see the waveforms of the semiconductor devices, the diode and the switch. While we are at it, we will also see the other waveforms so that we will have a complete picture. This is the circuit diagram again. So the inductor current waveform we plotted earlier starts from I1, goes to I2 at the end of the T-on interval, and then comes back to I1 at the end of the T-off interval. The average of the inductor current is the output current. The output current, remember, it is placed midway between I1 and I2. We also saw the VL waveform. VL waveform swings from Vin minus V0 to minus V0. The value of VL is Vin minus V0 during T-on interval and minus V0 during T-off interval. The inductor current flows through the switch during the T-on interval and flows through the diode during the T-off interval. First, let us consider the diode current. The diode current is the part of the inductor current that flows during off interval. So if you take the part of the inductor current during off interval, that will be the diode current. We have plotted it here. This value is I2, this value is I1, so this will be I2, this will be I1. We will now plot the diode voltage waveform. When the diode is on during T-off interval, the diode voltage will be 0. We are assuming an ideal diode. When the diode is off, switch is conducting, then the cathode of the diode is connected to the plus terminal of the source and the anode of the diode is connected to the minus terminal of the source. So the diode voltage will be equal to minus Vin. Remember, the reference polarity for diode voltage is always anode positive and cathode negative. So a reverse voltage is applied to the diode, so the diode blocks. The magnitude of the voltage is equal to the source voltage itself. Next, we can plot the switch current waveform. The switch current waveform is the inductor current during the T-on interval. A part of the inductor current for the duration of T-on flows through the switch. So when you switch on the switch, the current jumps to I1 and then it goes to I2 following the inductor current. And when you switch it off, the current falls to 0 and that I2 current jumps to the diode. And so the inductor current continues via the diode. So this jumping of the current from one branch of the circuit to another branch of the circuit, in this case from the switch to the diode, is called commutation. which is a common phenomenon in many places, including in DC motors. Here, the current jumps from the switch to the diode, and at the end of the T-off interval, the current I1 jumps from the diode to the switch. Again, that is an example of current commutation. Next, we will see the switch voltage waveform. When the switch is on during the T-on interval, of course, the switch voltage is 0. When the switch is off, the diode is conducting. The diode voltage is assumed to be 0. So Vin is applied across the switch. So I can plot the switch voltage waveform. It is 0 during the on interval, and during the off interval, the switch voltage is Vin. So we have plotted all the waveforms. This ability to plot the waveforms is important in power electronics because many times we will check whether the circuit is working properly or not by observing the waveform. When we observe the waveforms, we need to verify them against predicted waveforms. So ability to plot, calculate and plot the waveforms is important. Next, I will list the algebraic expressions for the various parameters of operation. First is delta IL. We have already seen that it is I2 minus I1 that equals V naught Ts by L, 1 minus D, and this is delta IL. Next is the value of I1 and the value of I2. The peak and valley values of the inductor current. You can notice that I0 is placed exactly in the middle, in this case, between I1 and I2. We already know the value of I0. So I0 minus delta IL by 2 is I1. I0 plus delta IL by 2 is I2. The next is the peak current in the semiconductor devices. You can notice that is I2 in the case of the diode and the same I2 in the case of the switch. ID peak equals IS peak equal to I2. Knowing this value helps you in selecting the proper devices. The switch and the diode must be able to withstand this peak current. We can also determine the average diode current that can help in choosing a particular diode. The average current is this area AD divided by the period Ts. This is a trapezoid. AD, the area AD is I1 plus I2 by 2 times T off. Notice that I1 plus I2 by 2 equals I0 because I0 is exactly in the middle of I1 and I2. So AD will be I0 times T off, and T off is 1 minus dTs. dTs is T on, 1 minus dTs is T off. So the area AD is I0 times 1 minus dTs. When you divide that by ds, that will give you the average diode current. And the average diode current is I0 times 1 minus d. This will help in the selection of the diode. This is the average diode current. Likewise, we can determine the average switch current. And the switch current will be this area AS divided by 1 period. AS is the area of this trapezoid, that is I1 plus I2 by 2 times T on. Once again, I1 plus I2 by 2 is I0, T on is dTs, so this is I0 dTs. When I divide that by ds, I will get I0 d. This line here is the average switch current. So IS average is I0 d, ID average is I0 times 1 minus d. So notice what is happening here. The average IL is the same as I0, the DC current. Switch is on for the fraction d in a period. The switch average current is d times I0. The diode is on for the remaining 1 minus d fraction of a period. The diode average current is 1 minus D times I naught, which is the average of the inductor current. Next, we will determine the peak voltage stresses. So you see the things that we are determining are all useful in selecting the devices. So power electronics analysis tends to be, like many engineering analysis, design-oriented analysis. So the diode peak inverse voltage is Vin. You just take the magnitude. It's a negative voltage. The magnitude of that is Vin. And the switch forward voltage is Vin. Notice that the diode is required to block a reverse voltage while the switch is expected to block a forward voltage. This is the case in many circuits. Next we will see the input current and the input-output power balance. I have plotted the inductor current waveform again here. The average of that is the output current. And the inductor current during the on interval, that is the switch current. I have plotted the switch current here. Notice that the switch current and the input current are the same in this case because the switch is in series with the source. So the average of the switch current is the same as the average of the input current, which is the DC input current. So IS average is IN average equals IN, that is the DC current. We just now determined the switch current average, which is this area AS divided by the TS. Area is given by I1 plus I2 by 2 times T on divided by TS, and we showed that that is equal to DI naught. So the average DC input current is DI naught. Now let us calculate the average input power. Average input power is average of the instantaneous power, and that is equal to 1 over Ts, 0 to Ts, P in, that is the instantaneous power, that small p is to show that it's a time varying function, dt. For any periodic waveform, we need to determine the average by taking 1 over Ts integral 0 to Ts of that function. So the instantaneous power P in is given by the voltage V in. V in is a constant value times I in. I in is fluctuating. So 0 to Ts V in Is dt. Is and I in are the same. V in is a constant value. I can take it out of the integral. So that will be V in times 1 over Ts integral 0 to Ts Is dt. This part is the switch average current or the input average current. So this will be V in times I in. V in is the applied DC voltage, I in is the average input current. So that's kind of obvious, but what we are showing is that even though I in has all this AC part, it is only the average part that matters for average power. As long as the input voltage is constant DC, this is valid. You can just take the current, take its average, neglect the ripple or the AC part, neglect the switching fundamental and its harmonics, take only the DC part, multiply it by the DC voltage, you will get the average power. Likewise, in another situation, if the current is a constant current and the voltage has a DC value and an AC part, you can leave the AC part, multiply the average voltage, which is the DC part of the voltage, with the current. Remember, IN is the same as the switch DC current or the switch average current, and we showed that that is equal to DI naught. So this will be V in DI naught. So the input power is V in DI naught, but V in D, remember, is output voltage because V naught is dV in under continuous conduction mode conditions. So P in equals V in times average input current, which equals output voltage times output current. What we have shown is the average input power and the output power, they are both the same. It has to be like that because we are assuming ideal lossless operation. There is no component in this ideal circuit where power dissipation is occurring, but we are verifying that. Ideally, we have shown that the efficiency is 100%. P naught equals P in. You consider this part, V in I in equals V naught I naught. All the quantities are DC quantities. This looks very familiar. If you take an ideal transformer, neglect the magnetizing current, neglect leakage inductances and other stuff, then V2 by V1 equals I1 by I2 equal to N turns ratio. Notice the similarity between these two equations. V0 by V in equals I in by I0 equals D. V2 by V1 equals I1 by I2 equals N. They are both similar. So the DC-DC converter works like a transformer, but for DC. So it works for DC, and also in a typical transformer, N is a fixed quantity, whereas here you can continuously vary D. One way to think of a DC-DC converter is that of a DC transformer with an adjustable turns ratio. It's not true only for buck converter, it's true for all DC-DC converters. Next, we will see a straightforward example of plotting the waveforms. This is the circuit diagram. The specifications are given as follows. V in is 400 volts, L is 4 millihenry, C is large. Unless you are calculating the ripple voltage, you don't need the C. You just need to assume that it is large so that the DC voltage is constant. RL, the load is a resistance and it is 24 ohms. Sometimes in working out the design, you may consider the load to be a resistance. It doesn't mean that you actually take a resistance and connect it to a DC-DC converter. In most instances, you won't be doing that. This is only to represent something that draws current and consumes power. The switching frequency is 20 kilohertz here and D is 0.6. So we can calculate the output voltage. We can show that the operation is in continuous conduction mode. Let's assume that it is in continuous conduction mode. The switching period Ts is given by 1 over Fs, 1 over 20 kilohertz, 50 microseconds. So T on is 0.6 of that, 30 microsecond, and T off is 0.4 of that, 20 microsecond. Next, we can calculate the output voltage V0 is dV in, which is 0.6 times 400, that is 240 volts DC, ideally. I0 is output voltage divided by RL, that is 240 volts divided by 24, 10 amperes. Again, you should note that the output voltage under CCM, at least ideally, does not depend on the load. We can calculate delta IL, peak to peak ripple current, V0 Ts by L, 1 minus D. Plug in all the values, you will get 1.2 amperes. When you know that the peak to peak ripple current is 1.2 amperes and the load current is 10 amperes, you know that what you have assumed that it was operating in CCM is correct. Because delta IL by 2 is 1.2 by 2.6 amperes, that is less than 10 amperes. As long as delta IL by 2 is less than 10 amperes, we are in CCM. We can calculate I1 and I2. I1 inductor valley current is I0 minus delta IL by 2. 10 minus 0.6, 9.4 amperes. Likewise, I2 inductor peak current is I0 plus delta IL by 2, 10.6 amperes. And then the diode average current is I0 1 minus D. We just now saw that. I0 is 10 amperes, D is 0.6, so it is 4 amperes. Likewise, IS average is I naught D 10 times 0.6, 6 amperes. Now we will plot the waveform. The TS period is 50 microsecond, T on is 30 microsecond, T off is 20 microsecond. The inductor current is as shown. The delta IL we calculated, peak to peak ripple, is 1.2 amperes. And the average of the inductor current is the output current I naught, 10 amperes. The average current is right in the middle of the peak and valley current values. So I1 will be 10 minus 0.6, 9.4 amperes. I2 is 10 plus 0.6, 10.6 amperes. The inductor voltage waveform is as shown. We already seen that. When the switch is on, the inductor voltage is Vin minus V0. Vin is 400 volts, V0 is 240 volts. So Vin minus V0 is 160 volts. When the switch is off, the inductor voltage is minus V0, minus 240 volts. You can notice that the waveforms are not to scale. The ripple current waveform, for example, has been exaggerated just to make the waveforms clearer. The diode current is nothing other than the inductor current during the off interval. So we can draw the diode current as shown. The value of the inductor current here is 10.6 amperes. So the diode current starts from I2 equal to 10.6 amperes and goes down to I1 equal to 9.4 amperes. So the average diode current, we have calculated it 10 times 0.4, 4 amperes. We can plot the diode voltage waveform. When the switch is on, the diode voltage equals minus 400 volts. And when the diode is on, of course, the diode voltage will be 0. By looking at the waveform, we can know that the diode is stressed to 400 volts. So the ideal maximum inverse voltage on the diode is 400 volts. Actually, in the circuit, it will be larger than this because of voltage spikes due to parasitic inductances. Next, we will see the switch current. Switch current is the same as the inductor current under T on interval. So we can plot the switch current as shown. It starts from I1 equal to 9.4 amperes and then goes to I2 equal to 10.6 amperes where it is switched off. And the average switch current will be D times I0, 0.6 times 10 amperes, 6 amperes. We can plot that also. Lastly, we can plot the switch voltage waveform. When the switch is on, of course, the voltage is 0. When the switch is off, as we saw, the switch voltage will be equal to Vin. So the voltage is 0 here and then voltage goes to 400 volts here. So in this video and in the companion video, buck converter CCM part 1 video, we saw the basic operation of the buck converter under continuous conduction mode. We saw the waveforms, we saw what the output voltage is, we saw the ripple current, we saw the ripple voltage, capacitor ripple voltage, and then we also saw how to plot these waveforms given the specification so that they can be useful in design and testing. With this, we have come to the end of the video. In case you find this video and the series of videos useful and interesting to you, please do consider subscribing to this channel and also clicking the like button. Thank you.